So can you all see my screen okay?
Yes.
Super. Okay, thank you. So hello again, everybody, and so welcome to this sixth lecture, which is going to be about accessing and transforming marine data. So my name's Sally Close. I'm from the University of Western Brittany. So to begin with, the kind of motivation for this lecture. When we want to use marine data, normally we have a specific purpose in mind for the reason that we want to use it. So for example, here, if we imagine that we're Jacques Cousteau and we're dreaming about making some kind of figure of the temperature in a certain region of the ocean, and maybe we're going to download some data from the internet in order to make this figure, this analysis that we want to get information from. So the thing is, we're thinking about this figure that we'd like to make in the way that humans think about things. But the marine data server, it looks like this, right? It's a series of computer storage units that are connected to the internet. So the big question for us is, how are we going to communicate with this data server, which is not really thinking, right? It's just producing ones and zeros. So the big question is, how are we going to get hold of this data and transform it in such a way that it's useful for us to do the scientific analyses that we want to make? So this might sound like it's not going to be such an interesting topic. Oh, but in fact, it's also a kind of history of oceanography, as well as being just a subject about how to access data. So in fact, I wanted to start by talking to you a little bit about the different types of data that we might want to access. So, oh, there's somebody.
I think someone has their mic open.
Oh, okay. Okay. So from the kind of different types of oceanographic data that we can have really evolved over time. So in the past, we didn't have very much data. So this question of how we should access and transform data didn't really exist because the quantity of data that was available wasn't enough that we needed to worry about how to treat the data. So in the past, there was much fewer data available. So by comparison with meteorology, there was much less data. So on the right-hand side here, this figure is showing us one of the earliest methods of collecting meteorological data, which is with a weather balloon. So if you're measuring the weather, you can just go to a given place, release the weather balloon, and it's quite easy to have data. If you want to collect data about the ocean, you need to go there in a ship, and that's really expensive normally. So for a long time, there were very few ocean measurements available. And that meant that a lot of the fundamental quantities about the ocean weren't known until relatively recently. So, for example, if we think about something like the quantity of heat transported by the ocean, which is a really fundamental quantity for the climate, the first estimate of that was actually only made in 1982. Until then, we didn't even know how big the size of that transport should be. So oceanography is a very young science, and this problem of having to deal with very large amounts of data is really a very recent problem, kind of the last 10 to 20 years that it's become a problem. So early ocean measurements, so this, the man that you can see on the top there leaning over the side of the ship to take a water measurement. So maybe you can see he's got this kind of long tube that he's going to put into the ocean and take water out. This was in the 1930s. And in fact, the way that we measure the ocean now to take high quality measurements hasn't really actually changed that much in terms of the actual process that's behind it. So the figure that's on the right in colour, where you can see an instrument, is what's called a CTD. So that stands for conductivity, temperature and depth. So it's a type of instrument. You can maybe see there's lots of these cylinders similar to the one that the man in the photo on the left is holding. And they're going to do the same thing that the man on the left is doing. So they close and they trap water inside that's then brought back up to the surface. So fundamentally, the way that we measure the ocean has remained similar. What's changed is the quantity of measurements that have become available. So up until the 1990s, to take these measurements, we still had to go out in a ship. And in fact, that meant that the number of measurements that were available were kind of the order of maybe a few tens of measurements a year. So there'd be a few tens of maximum of ships that would go out and take measurements along one of these red lines. So these are regular sampling lines. And so during the 1990s, people were becoming more aware about climate change and these kind of things, and they decided it would be a good idea to make a kind of map of the current state of the ocean. So measurements were taken along all of the red lines that you can see in this image over the course of 8 years. So this was a big program at the time. It was the largest, one of the largest kind of large scale oceanographic collects of data that had existed until that time. So that was kind of 10 years worth of work. And then in the late 1990s, a new type of instrument called the Argo float was developed. So this was based on earlier kind of ideas that people had had since the 1950s, that it would be much more cost efficient if we could have robots to measure the ocean for us, because what's really expensive when you're making these measurements is the time that you're spending on the ship. So to run a research ship is very, very expensive. So people had kind of realized that if we could take that ship part out of the equation and have these robots that would measure the ocean for us, that could make the number of measurements that were available much larger. So this man that you can see on the left in the black and white picture was working on an early version of these kind of floats back in the 1950s, where he was building a kind of prototype version using just tubes and various simple pieces of electronics. And the kind of final result of that in the late 1990s and early 2000s is the image that you can see on the right. So these yellow instruments, like the one that the two people are holding, we now just kind of throw into the ocean and they drift with the currents and take measurements every 10 days. And that really revolutionized the quantity of data, observational data that was available. So initially, when the program was developed, the idea was that we could have 3,000 floats in the ocean at any one time, and they would kind of give us a good coverage of the state of the ocean. That number was achieved in 2007. And the current state of the Argo float coverage looks like this. So this is taken from February 2025. So all of the different coloured dots that you can see are the positions of one float in 2025. So there's 4,137 floats working at that instant. And each of the different colours is for a different country. So it's really a global effort. All of these different countries contribute by providing floats for this programme, which then just drift with the currents, and the data is sent back via satellite every 10 days. So floats continue to evolve. We've got more and more of them. They can measure more and more things. Some of them can measure biological and chemical variables. Some of them can even survive in the polar regions. So with that evolution, the amount of data that was available continuously dramatically increased. So that's over the last maybe 20 years. At the same time, we've also had new satellites that have been launched. So that was since about the 1980s. So we have access to more and more variables that cover the whole ocean surface and that are measured from space. So again, that's an increasingly large quantity of data. At the same time, another source of data that we use, these numerical ocean models, are going towards higher and higher resolution all the time in terms of the spatial resolution. So in the early climate experiments, they used to be run with a 4-degree grid. Some of them now go up to a 1/12 of a degree for climate size simulations. And if we're running a model with just the ocean, that could go up to a 60th of a degree even. So it's really a huge improvement in what we can resolve in terms of the ocean, but also a huge, huge increase in the quantity of data that's associated with that. So that means that over the past 2 decades, particularly, the amount of data has really increased exponentially, and that's continuing even at the present day because models are always going to higher resolution, satellites are always going to higher resolution. So this has really led to changes in how we have worked with and how we are currently working with data, which is something that's very much always evolving. So the plan for the topics related to this that we're going to talk about today are really going to be trying to answer these 2 questions. So firstly, we want to know, how is this data going to get from somewhere else on the internet to you for you to be able to make your analyses? And secondly, we want to know if there's anything particular that we need to think about when we're trying to retrieve these data and when we're working with them. So the first question of how the data is going to get from somewhere else on the internet to you depends on a number of things. So it's going to depend on what kind of data you want to retrieve. So depending on whether you're working with data from an individual instrument or data from a model or from satellites, that's going to change how you access the data. It's going to depend on where the data is stored. So how are you able to access that data? What's the kind of interface by which you're going to be able to access that data? And it also depends on where you want to process it. So will you be performing the analysis on your computer individually? Will you be performing it on somebody else's server? Will you be performing it on in the cloud? So this is these are all going to affect how you access the data. And the other things that you might need to think about when you're deciding if you have a choice about how you're going to access the data, things that might influence your decision are going to be the size of the data set that you're trying to retrieve. So that's going to, again, vary depending on the choice of data or the type of data that you're using. It's going to depend on the format of the data. So are you using data from an individual point? Are you using data that's on a grid? Is it binary format? Is it text format? And it's also going to depend on the problem that you're trying to solve. So do you need lots of different variables? Do you need global data or just a certain region? So all of these different things are factors that are going to address how you're going to access the data. So the plan for the different topics that we're going to talk about is this. So we're going to start by looking a little bit at web scraping, which is kind of the most generic method for accessing data generally. We'll then talk a little bit about the process of what we call data wrangling. So it's the process of formatting data, changing it so that it's going to be in a format where you're ready to be able to calculate with it. So you need to maybe transform the data a little bit before you can make the calculations that you want to make. And then we'll talk about some more modern methods of working with data. So we're going to introduce the idea of API, which are kind of software messengers that allow different pieces of software or different computers to communicate with one another. We'll then look at a specific type of API that's very common in the earth sciences. So it's a method that you're quite likely to meet because it's used by a lot of different data servers. And finally, at the end, we'll talk a little bit about cloud computing. So this is a relatively new way of performing calculations that's quite well adapted to working with large volumes of data. So it's for cases where we don't want to have to bring all of this data back to our own machine. We might prefer to perform the calculations somewhere else so that we can reduce the volume of data in the result and then just bring a reduced part of the data back to our computer. So the use cases are generally that the first two would be used in situations where we're working with relatively small amounts of data. So the data is often not well structured and we might need to perform more pre-processing to get it into a format where we're able to analyze it. For the two middle parts, for the API and the Open DAP, it's for working with larger amounts of data normally. So often these data will have been pre-formatted so that they'll be on a grid or that they'll have they'll have a fixed format in place already. These can be types of data that are normally a bit larger than the quantity of data you would be dealing with if you're collecting the data yourself from a website. So in these cases, normally you would still be storing and analyzing the data on your local infrastructure, but that might even be bigger than something that you would want to store on your own computer. So you might be storing it on a computer in your lab, for example. And cloud computing is really for if we're working with huge amounts of data. So in that case, normally it's going to be gridded because it's going to be coming from a model or a high resolution satellite, for example. So this is a case where the data will be too large for you to analyze locally. And normally you'll make that decision to perform the analysis on somebody else's computer instead. So that's the plan for what we're going to talk about. If you've got any questions, don't hesitate as we're going along to ask them if you see something and you're wondering about it. Okay, so let's start by talking about small amounts of data. So for this first part, we're going to talk about how to get unstructured data or how to deal with unstructured data or kind of mildly structured data that you might encounter if you're working normally with specific instruments. So this term that we call web scraping is the process of extracting information from a website. And normally we can do that either, it could be something as simple as kind of clicking and downloading a text file. It can also be automated. So it could also be that if you know that there's a series of websites that have specific information that you want to extract, you might choose to automate the process of extracting that information from those web pages by processing the raw code of the web page. So this is not generally a simple exercise. So normally you would need to understand what the structure of the web page is if you want to do this. You would then either write a program or use a piece of software to extract that piece of information that you want to remove from the web page. So the program will perform that transformation to extract this piece of information, and then you're either going to store that information and move on to the next web page that you want to extract information from, or you're going to process it as you're going along. So as an example of a kind of use case for that, if you want to extract kind of lots of information that's not available anywhere else. So if you would kind of your only other way to access the data might be, you know, copying and pasting by hand or right-clicking and downloading the data file. it's a case where you might make an error, kind of human error, if you're repeating that process a lot. So that could be interesting to automate the process in that case. If you want to store and archive the data, so it's information that you could just keep copying and pasting, but you want to have a copy locally, you might choose to apply this method. But really the main reason that you would choose to go through all of this process would only be if there isn't an easier way to access the data. So this is really the most intensive method that you could imagine in terms of the effort that you would supply in order to access data. So reasons that you might not use this, the first one might be that in fact you're not allowed to. So some websites will specify that you can't automate the process of extracting this information. So we'll talk about that in just a second. But in fact, the main reason that you would choose not to use this method would be if you have an alternative option. So that would be using an API. So that's what we'll talk about next. So this really kind of want to emphasize that if you have any other option, don't bother with web scraping because it's a very difficult, intensive process. So an example of how you could use this kind of method, if you've ever tapped into Google a request for kind of local information or something like a weather report. So if I've put in earlier, for example, today, I put in today's tides in Brest to find out what time the tides were in Brest today. And the format, before it gives me all of the results for the different web pages that I could look at, you may have seen that Google can provide you with a little summary of the information that it thinks that you'll be looking for before it provides you with the search results. So if I put that for Brest, it provides me with a little summary of what the times are today in Brest. And in fact, if I change the name of the town, so if I put in Gdansk instead of Brest, it's going to give me the same format of information. So it's again given me this summary of what the tide times are in the same format as we had, if I go back for Brest here. So one thing that we can see between those two searches is that the information is similar, right? So here we've got the type of tide, was it high or low? We've got the time and we've got the height of the tide. So that came from a website that was called Tides Today. The request for Gdansk doesn't come from the same website, right? So that's showing me information that's been taken from a different website. So it's come from tideforecast.com. So the information is still similar, but we can see that the format's not exactly the same as the one that we had for Brest. And if I put in Valletta, we can see that the format is different again. So we can see that we've got another different website. We've got the same information again, but the format's not exactly the same as for the other two examples. So this is Google pre-processing the information for us to present the information that it thinks that we want at the beginning of the search results. And that's an example of something that we could exploit if we wanted to do web scraping. So in fact, this little table at the beginning is always presented in the same format. So that means that in fact, the name for this part of the web page in the code is always the same. So it's possible to look at the code for this web page to identify the piece of information that's associated with this table. And based on that, it would be possible to download this information automatically by writing a program to do that. You can only do this. So this is this file that I've just explained to you exists. You can only do this if the website owner agrees that it's okay for you to do so. So the way that they do that is with this file that's called robots.txt. So robots.txt is a file that exists on all web servers, and it tells you what you can or can't do with respect to that web page. So it's a piece or kind of a series of instructions that are meant to be read by web scrapers. So this is this software that's going to extract the piece of information for you. And it'll tell you whether or not the site owner thinks it's okay for you to automatically extract information from their website. So they might not want you to do that, either because they don't want people to store their information, or because in fact it's quite intensive for the server if it has lots of repeated requests trying to extract information. So web scraping software, if you're using software to do this, will normally have options that will allow you to specify that it should look at robots.txt, and you always should. The main reason for that is if you don't respect the owner's wishes, you might find yourself actually blocked from the website. So in that case, you have no future access to the data that you were trying to get at all. Okay, so for web scraping, the main things to keep in mind are that it's kind of the most generic, it's the term for the most generic way to access information from a web page. So that can be any format in which you're interacting with the web page automatically to download either files that are on the web page or to extract parts of the code automatically. It's the most generic method for extracting data from websites. So it's widely used in data science, not just in oceanography. So it's quite flexible. It's fairly efficient, but it's really, really demands a lot of effort for the setup if you kind of aren't familiar with the method. So you need to write the program yourself, or you need to set up for your specific configuration yourself. If the owner of the website changes the website, your code will stop working. So that's another disadvantage. So you need to make these changes. And also, you're going to need to work out not only how to get the data out of the website, but also what you're going to do with it afterwards. So the main message is, if you don't have to do it, don't. So the process is something like this, right? We were thinking about this figure that we wanted to make, this temperature plot. We would then pass by the web scraping software to get hold of the information that we wanted. That's going to give us back eventually the raw data that we've extracted from these web pages. So what do we need to do then to get it into a format in which we're going to get something that looks like this nice analysis that we've been thinking about performing? So the answer to that is data wrangling. It's this process of transforming the data to get it into a format where it's ready for use. So this data wrangling is, again, like for web scraping, it's going to depend on the type of data that you're treating. So in fact, there's not a kind of generic set of processing steps that you would need to perform in order to be able to transform any data type. So it's really just the generic term for cleaning up the data so that your software or your program is going to be able to read the data from the input files. So if you've got the data yourself, if you've compiled it yourself from different web pages, you're most certainly going to have to do this step. But you might also have to do this step if you're downloading data from an oceanographic data center. So it's particularly going to be true if you're working with data from individual instruments. So we're going to see an example with tide gauge data in just a second. So it's particularly true for non-gridded data. And the kind of steps that you might need to take might be removing extra information that's included in the data files that's not relevant for you. So there might be headers or there might be extra text within the data file that's going to make it more difficult to read. There might be missing values within your data. So that might be something that you need to replace with a fixed value or to take out of the data. You might need to work out how to deal with kind of fixed format data. So the data might be in a number of fixed columns or fixed rows. And also you might need to combine multiple data sources. So potentially you could have different files that have different formats. So let's look at an example for that with data that's come from an oceanographic data center. So if we think about trying to use data about the sea level, so on the photograph on the right, you can see that the yellow instrument is what's called a bottom pressure recorder. So these are small instruments that sit at the bottom of the ocean, and they measure the pressure weighing down on that instrument. So it's a measure of the oceanic mass above the instrument. So that can tell us something about sea level, for example. So this example that we're going to look at is taken from, so the link that you can see down below here. So it's the Permanent Service for Mean Sea Level, it's PSMSL. So they're a website that provide access to data from tide gauges that measure the sea level, and also from bottom pressure recorders globally. So it's a good way to access this type of data. And so the instrument that I've chosen is taken from Drake Passage. So that's in the Southern Ocean, just above Antarctica. So between Antarctica and South America. And we've got the little map here, and we can see the green arrow, which is pointing to the place at which the instrument was sitting. So we've got some information about the data that's available here. So we've got the latitude and longitudes of the instrument. We've got the time at which it was first put in place. So it started taking measurements in 1992, and they've got data until 2013. And then just underneath, in the section that's called All Data, we can see a map of the readings that have been taken by this instrument. So we've got different colours because the instrument's not the same instrument that was put in place in 1992. So that means every year or every few years, they've gone back. Somebody who put the instrument there has taken the instrument out again and checked on whether it's still working or they've replaced it. So it's not a continuous data record. It could be several different instruments that have been replaced one after the other. So we can see that there's some gaps in the data record. So between, I don't know, it's maybe in about 1998 or 1999, there was no data. And then between about 2001 and 2004, again, there's no data that's been left at that place. So if we want to use this instrument, we're going to have to deal with missing data, and we're also going to have to deal with combining a number of different data files to make one continuous record for the measurements taken at that place. So this is the top part of this website that you have the link for on the right. If we look at the lower part of the website, it looks something like this. So the bottom part of the website shows us a table with all of the different files that are available for this instrument. So we can see that they've got each file is going to contain data for approximately 1 year. We can see that they don't always manage to put the instrument back in exactly the same place. So if we look at the different values of the latitude, it's more or less the same, but it changes a little bit over time. Same for the longitude. So associated with those small changes in latitude and longitude, we've got changes in depth because the seafloor's not perfectly flat. So that's going to be another little thing that's going to change from one file to the next. And we've also got choice about the different type of data that we might want to download. So we might choose to have data with an hourly resolution, with a daily resolution, or we might choose to have just the tide data for that instrument. And we can also see at the right-hand part of the screen, we've got the option for the metadata. So the metadata is kind of supplementary information that's going to be associated with the data files that's going to be useful for us to know about. So we're going to see an example of that in just a second. So we've got a list of all the different dates that are available on the left. So we can see that as we suspected, there's a gap in the data between about 2000 and 2003. So that's something that we might need to take into account. And if we look inside one of these files, it's not working. There we go. So if we download and open up one of these text files, we get something that looks like this. So we can see that at the top of the file, we've got lots of kind of free format text information. So we've got a description of what the data is, what the time resolution is. We've got information about where it was deployed. We've got the name of the center that was responsible for deploying the instrument. And then we've got information about what we're seeing or what the numbers in the following part of the file mean. So we've got a description of what each column stands for. So we can see that in the second column, the one that's called FL, we've got information about whether the data is good quality or not. So again, that's something that we might want to think about when we're processing the data. So before we can treat this data with a Python program, or before we can import it into Excel, for example, we might need to do prior processing of this data. So we would want to get rid of anything that's not in a kind of uniform format that we can deal with. So all of this information at the beginning of the text file that's useful for us as human beings to know what the numbers mean in the rest of the text file is helpful information, but it's difficult to read for a computer program because it's not conform with the following part of the file, which just consists of 8 columns of numbers. So we might need to remove all of that text in the beginning before we can actually process the data. We might then want to separate out the different variables in the different columns. We can also see that we've got a value for the missing numbers. So these values of minus 999.999 are telling us that the instrument wasn't returning measurements for those quantities at that particular time, so on the particular day and at that particular hour. So there's a kind of a fair amount of things that we need to clean up within the data file before we can use it. And we also need to do that for every single file. So if you remember, we had a whole table with a list of files, and we would need to make that pre-processing for all of the files before we can actually start working with the data. So we had that last column on the right that was called metadata that we could access for the files. And this is an example of the metadata that was associated with the data file that we were trying to download. So the metadata is descriptive information about things like the data quality, about whether any pre-processing's been performed. It can be any information that the data provider thinks you might potentially need to know. So it could be information that could affect how you interpret your analysis afterwards. It could be information that's just useful to help you understand what's in the data file. So here, for example, we can see that we've got information about the location, about the time period, and then they're telling us that they've already applied a correction to the data. So we can see that they've removed 103 bars worth of pressure from the raw pressure data. So presumably they decided that the instrument had some kind of bias relative to what they considered to be the truth. So if we're combining lots of different instruments, that might be something that's useful for us to know about if we think that maybe the mean value that's coming from that instrument or from that part of the data record might not be perfectly precise. So the metadata might be useful, it might be not. Normally, it's fairly easy to interpret, and you'll make that decision based on what you're trying to do with the rest of your analysis. Okay. So if we wanted to transform this data file into a process where point where we'd be ready to use it, either we can go through all of those steps that we've just talked about by hand. So before we would read in each of these data files, we would delete all of this text at the beginning. We would load the new text file that would start with the number 1, so the part at which we have the line 1/1/1992. We would start from there and read that into the software program, and then we would decide what we wanted to do about the missing values. That's the more intensive way to do it. In fact, if you're used to using Python or other programming languages, often when you're reading in CSV files, so this is the comma-separated variable format, there are often options to do part of this pre-processing directly. So you can choose to skip a certain number of lines at the beginning of the file, for example. So if we look at a second example for a different type of file from the same data center. So this is now a tide gauge file. So again, we've got the picture on the top right of the screen is showing you what a modern tide gauge might look like. So it's this big metal tube where water comes into the bottom, and there are sensors inside that measure how high the water is within that big metal tube, and that's recorded electronically. So if we look at a nearby tide gauge for the measurement that we just looked at, that bottom pressure recorder, we can see that this time, so we've got the location of the instrument at the top again. So we've got Ushuaia in Argentina. And then underneath, we can see that we've got already some information that's telling us that the data can potentially have problems. So we can see that we've got warning, QC flag exists, please read the documentation. So QC flag is quality control flag. So often, if you're working with data from individual instruments, you would have some kind of assessment of the quality of the data that's supplied with the data. So the format again looks fairly similar to what we've just seen for the bottom pressure recorder. So we've got information about the position, about the time span of the data. We've got a percentage completeness, so that's telling us how much missing data we can expect to see within our data. And we've got the date at which it was last updated, so it's a historical series of data. Compared to the last data, so it's on the same website, but we can see here that the resolution in time of the data is not the same as for the last instrument that we looked at. So just because it's coming from the same website doesn't mean that we're necessarily going to have the same options for each individual instrument. So here we've only got access to monthly data. And we can see that again, there's some missing data in terms of the data coverage. So if we look at the metadata for this one, we can see that it's different from the last file. So we've got information this time about some pre-processing that's been performed to the data and about what they think we should do to this data if we want to use it, for example, in combination with other instruments. So they're telling us here, so the first line is telling us general information about the instrument. We've then got in the middle, it's telling us that they've noticed that there was some kind of shift in sea level when they've changed the instrument in the 1970s. And then at the bottom, they're telling us about the correction that they think we should apply to this data if we want to combine it with other instruments. So this is why it's always a really good idea to check the metadata before you start processing the data. It's because there could be this kind of correction that you should apply to the data. And if we don't apply that data, we might not make a good interpretation of our results at the end. So it could be that we didn't apply this correction. We have a shift in the data and we interpret that as a rise in the sea level that was due to climate factors, for example. Whereas in fact, here they're telling us that it's probably just due to a problem with the instrument. So it's always a really good idea to check this metadata before we start processing the data, just in case. Okay, so the data format for this file, so we saw it was monthly data rather than hourly data this time. Here we can see that it's quite different from the last data file that we looked at. So again, it's coming from the same data center that's kind of being supplied by the same source, but the format of the file that we're getting back is not the same. So again, we're going to have to pay attention to the fact that different instruments have different file formats. So here we can see that instead of having text information at the beginning, giving us information about the file, we've just got a series of 3 columns of numbers. We can see that the time information is now contained just in one series of numbers. So we've got the year expressed as a fraction. So it's now giving us 1970.3750. So that we would need to treat that data or treat that number to make it back into a format that we can understand as humans. And we can also see that the value that's representing missing data isn't the same as in the previous file. So previously it was minus 999, here it's minus 99999. So again, we're going to need to take that into account during the pre-processing. So there's an advantage with this type of file where it's just numbers, which is that we have to do less work beforehand, so that you could probably just read this file directly into your software and it would work straight away. The disadvantage is that if you haven't saved the metadata with this file, if you just save this file on your computer and you call it Ushuaia.txt, you go away, you come back a few weeks later, you think, hey, what's this file? Probably you won't know anymore because you've got no information in the file aside from a series of numbers. So there's an advantage and a disadvantage to storing the metadata separately from the file. One of them is that the file is easier to read. You can just treat this file directly in your computer. The disadvantage is that for a human being, if you haven't got information stored with it about what this file is, you don't know what it is, right? It's just a series of numbers. So the metadata is important from that point of view. And if you're downloading this kind of text file and not treating it straight away, it's maybe a good idea to download the metadata at the same time so that later you know what you're dealing with if you come across the file again. Okay, so for data wrangling, if we want to summarize, it's probably one of the most boring parts of data analysis, really. So often it's this manually cleaning up the file, getting it into the format in which you're ready to start your analysis. Unfortunately, if you're dealing with data from individual instruments or data that you've collected yourself, you're probably almost certainly going to have to do some of this preparation. And that's the same actually if you go out and collect data on a ship. There's always some kind of pre-processing that you have to perform to get the data into a format where it's ready for other people to use. So that's often the case for individual instruments, but in fact, there are lots of other different types of data where we don't have to do all of this preparation. So for data that's gridded, so that could be satellite data, it could be observations that have been pre-processed by somebody else, or it could be data that's from a model. We wouldn't have to perform this type of pre-processing because the data are in a regular structured format. So these gridded types of data are normally in a specific type of format. So they're in a format that's called NetCDF, which is a very common data type in oceanography. And the advantage of this data type is that it lets us store metadata along with the actual data. So we're never faced with this problem of what's this data file? What are all these numbers? Because in fact, that information is stored with the data. So it means that we always know what those numbers are. So a lot of oceanographic software or oceanographic tools are very well equipped to deal with that type of data format. So in fact, you might be able to completely escape doing any of this pre-processing at all, if you're lucky, because it might come in this format where everything is already labeled and has already been put into a nice format that's kind of coherent and the same from one data file to the next one. And the good news is that for almost all of the data that you might want to download from a marine data center, you'll be able to do so in NetCDF format. So let's start thinking about these kind of bigger quantities of data now. If we go from small data to medium-sized data. So the question is going to be, how can we get data from a data center? So the main methods that we're going to look at for doing this are firstly via API as a kind of generic idea, and then we'll look at these two methods that are quite commonly used by oceanographic data centers, which is the OpenDAP method and the threads interface, which is associated with that OpenDAP method. So we've got this specific kind of type of library that's a method by which computers can communicate with one another. And it's called API, which stands for Application Programming Interface. So the motivation is that the computer needs to know what you want. So the place in which the data is stored needs to know what you want. And then computer that you're using to communicate with that computer needs to do so in such a way that the two can understand one another. So if you think about using software, or if you think about using your computer or your phone, anytime you want to do something on your computer, the way for you to make the machine do what you want it to do is via software that's been designed in such a way that you can interact with it. So that's what's called the user interface. So it's the window system where you can click on buttons and type into the computer, has been designed in order for a human to be able to interact with the computer. And the API is exactly the same, but its role is to enable one computer to interact with another computer. So they don't need interfaces and buttons to click on. They just need a kind of a fixed set of instructions about how to talk to one another. So this API, how can we understand what it is? I like to make an analogy with going to a restaurant. So if you imagine that you've gone to a restaurant and you've decided that you want to eat pancakes, the way that you get to eat pancakes is by talking to the waiter and placing an order, right? So if you decide you want to eat pancakes, in most normal restaurants, normally the chef does not kind of throw your food directly at you across the restaurant from the kitchen, right? So this kind of process that we have here is not what normally happens in a restaurant. So normally you have to talk to somebody else. You don't communicate directly with the chef. So in fact, this process by which we would normally order food in a restaurant is that you start on the right, you're thinking that you'd like to eat pancakes. You talk to the waiter goes to the kitchen, the chef makes the pancakes, the waiter brings back your pancakes, everybody's happy. And in fact, the API in the process where two computers are talking to one another is playing a very similar role to the waiter. So if we change this analogy and we imagine that instead of the person who wants to eat pancakes, we have Google Maps, for example, that wants to know where you are with your phone. And it wants to get that information from your phone system, for example. So we've replaced the chef with your phone. So it's in fact the operating system that's going to tell it that information. The way that Google Maps is going to ask your phone, where am I, is via an API. So we've got a piece of software on your phone. It wants to get information that's stored in the operating system. It can communicate with your phone via an API. So it's this waiter that's passing information about what the application wants to your phone. So in fact, you might have already seen this. If ever you've seen on your phone something like this, where your phone asks you if an application can have access to your location or if it can have access to your file system. This is a sign that the API is working, right? When you see one of these activations, it's that this is Google Maps has asked the API to get this information from your phone. And this is your operating system saying, hey, is it all right if I give this information to the application? So when you see one of these alerts, that's what's going on. It's the API trying to communicate between an application and the operating system. And in fact, exactly the same thing is going to happen when we try to get data from a data center. So the type of API that's in your phone is not the same type of API that will be used for your computer to ask a data center for information. So there are hundreds of different types of API depending on the specific purpose that you're using it for, but also on the data center. So for example, if you try to ask for data from one data center and then you try to ask from a different data center, those two data centers might not necessarily be using the same API. So each data center will generally have its own specific API. So these are web API that we're going to be thinking about to get data from a different storage location. So from a data center that's storing these data somewhere. And they're useful because they allow us to pass very specific information to the data center about what we want to get back. So if we only want to take back part of the data, or if we only want to take back certain files, we're going to be able to specify that often via these API type commands. So but by giving information to our software, the API will then talk between our software and the final server, and we'll get back the information that we wanted to retrieve. So if we make an analogy now between, we look at the process of how we might look at getting data from a data server. So we're starting on the left this time. So we're still Jacques Cousteau, and we're still thinking about making this temperature plot, this density plot that we've been thinking about since the beginning. So in this situation, when we're thinking about making this temperature plot, we're like the man sitting at the table with the menu. So we're trying to think about what data we want to get back from the data server. So we're then going to interact with a piece of software. So in our case, it could be a data catalog interface. So we're going to see this threads interface shortly. It could also be a Python program that we've written that's going to say what type of data we want to get back. The API will then talk between our Python program or our data catalog interface and the data server, which is up here on the top right of the screen. So we've got our waiter that's going to communicate between those two. So this is our waiter. So he's going to talk, it's going to take the instruction from our program or from the threads catalog and communicate it to the data server. And then when the data server has prepared the data that we wanted, the API will then bring that back to either our data interface or our Python program. So that then gives us the formatted data that we've requested. So it's like we've got our pancakes finally from the kitchen after the waiter brings them back for us. And once we've got that, we can perform this analysis and make this map that we've been thinking about since the beginning. So why do we need to talk about API? It's because the data that we might be dealing with when we're trying to think about these larger volumes of data are more complicated in the sense that they might be structured or that they might be of a bigger volume compared to the kind of small amounts of information that we might be dealing with if we want to have data off a web page. So these data can be up to 4-dimensional. If you think about working with temperature or salinity data, you might have latitude, longitude, depth, and time to deal with. The data are often going to be structured. So if there is a large volume of data, normally that's because there's a lot of measurements. So there's either a full grid of ocean model output, or there's global satellite data coverage, for example. They probably have metadata that's associated with them. So as we've seen, that's something that we need to know about. And potentially they're going to be at large spatial scale. So it could be that you have a file that contains global data and they might have high temporal resolution. And probably you might not need all of the data that's available. All right, so if we imagine that you want to download some sea surface height data because you're interested in the Mediterranean Sea, it's annoying if you have to download data for the whole globe, whereas in fact you're only going to take out a small portion on the Mediterranean Sea to use, and in fact you're going to delete the rest of the data anyway. If you want a specific time resolution, for example, if you want an annual average, if there's a means for you to only download that annual average rather than having to download daily data and calculate that yourself, that can save you a lot of time. And similarly, if you're only interested in the top 50 meters of the ocean, it's annoying if you have to download data for the full 4,000 meters of the ocean, and then you're going to delete everything between 50 and 4,000 meters after downloading the data. It's wasteful and difficult to deal with. So to overcome that problem, the idea is that if we can have the computer and the data server communicate with one another and tell them, or the computer tell the data server that you only want part of the data, that's very efficient, because that means there's less bandwidth wasted in downloading data that's not going to be used in your final analysis. So in many cases, you don't need the full data. And often, in fact, in many cases, it's too much to work with, right? If you've got a very big data volume, you have to spend a long time downloading it, and then it becomes difficult to analyze because you're trying to deal with a large quantity of data. So these APIs are going to be libraries, these sets of instructions that we're going to tell the computer what we want. Often they interface with Python, but some of them are just kind of directly accessible via general software like Ocean Data View or Ferret or NCO. These kind of generic data tools that you might have already seen in some of the earlier lectures. So for ECMWF, for example, they supply, so these are people that supply, it's the European Centre for Medium Range Weather Forecasting. They supply analyses of the state of the atmosphere, available with lots of different time resolutions. They supply an API that can interface with Python, and they give examples of how you can use that. So for example, here, my app would be Python. It's going to communicate with the ECMWF data archive via this API. And here they give an example of what the format of your request might look like. So we can see there's lots of different qualities of the data that we can specify. So we can specify which data set we want. So they have lots of different data sets. We can specify the date range. We can specify whether we want to look at the surface or at different height levels. We can specify certain variables. We can specify what quality of data we want. So do we want operational data or research data? We can specify the time at which we want it, and so on. So we can specify very precise subsets of the data in these types of requests. So ECMWF give us one type of API, but as I mentioned earlier, in fact, each different data center has their own type of API. So if we look at marine data specifically, a lot of that's distributed by the Copernicus Marine Environment Monitoring Service. So they have a very big data portal where we can access lots of different types of data. So they provide a web catalog where we can either click and choose to download different types of data manually, or they also have an API that we can use to automate that process. So we're going to look at an example of how to make it easier to use one of these APIs. So for the ECMWF, so this is very similar to the example that we've just seen. So they give us examples on their webpage of how to format these requests if we want to use Python to extract the data. So if we wanted to extract a different variable, we would have to take this example and then adapt it based to exactly what data we wanted to download. For the CMMs, the Copernicus Marine Service, in fact, they have a very useful tool, which is that their website can automatically generate the script for you. So until you're kind of comfortable with writing these kinds of programs yourself, they can help you to do that by showing you or kind of creating the example for you. So I'm just going to switch to a different window if I can. So I want to go to this one up. Yeah. So if I go to, let's see, I want to change the window. So I want to look at this one. So if I go to the Copernicus Marine webpage, here we've got a particular product. So it's the ocean reanalysis. So it's like model output for the global ocean. It's at 1/12 of a degree and with 50 vertical levels. So it's a very big data set. And it's available from 1993 to the present day. So if I decide that I want to download part of this data, I definitely don't want to download the full data set because that's going to be absolutely huge. So if I want to download only part of it, I can click on data access over here in the corner. And I come onto this window where it helps me to navigate through what type of data I might want to download. So we can see we've got different data set types in the left column here. So I've got a choice of making daily data, monthly data. I've got different types of analyses. I can have climatology and I can have fields that are non-variant. So things like the bathymetry or the information about the grid doesn't contain time dependence. So I would only need to download that once, for example, if I wanted those variables. So if we imagine that I want to download daily data, if I click on form over here under subset, I come onto a window that looks like this. And in fact, in this window, I can see all of the different choices that I can make about how I might want to download this data. So I've got, similarly to before for those different instruments, I've got some generic information about the data set. And then I've got the choice of the variables that I can download. So I might not want most of these, for example. So let's imagine that I don't want all of those variables. And the thing that I want to download is actually, let's say I want to download the sea surface height. So I would just click that one variable there. And imagine that I'm working on the Mediterranean. So I've got this map here where I can select which part of the data I want to download. So I can draw a little box like that. It's very easy to select the region that I want to work on. And finally, I can choose a date range for the time period that I want to download. So I'm going to leave that one as is for the moment. So it's going just for the day of the 30th of June. So if I now come back up to the top, we can see on the right-hand side of the screen here, it's telling me how big that data file will be if I want to download it. So it's giving me already a size of an idea about how big the data will be. If I try to download too much data, let's do that. So let's add all of them, and let's imagine that I go up to let's say I'm going to try and download a whole year's worth of data. We can see that at the top of the screen here, it's telling me I'm trying to download too much data. So you see, you've got this red message that's appeared in the top of the screen here. It's telling me it's too much. It's not going to let me extract that much. So if I go back to 2021, so we've only got 1 day's worth of data. And now if I want to download the code that's going to let me interact with the API and download just this part of the data, I can click on this button here that says automate. And if I do that, it's going to give me this window that pops up that tells me either what command I need to pass to a tool that they supply to download that data. Or if I click on the right-hand button here, it tells me what the API command should be for Python if I want to download that data. So it's really handy because it's filled in all of these things that I've specified for me using the graphical interface automatically. So it's filled in all of the variables that I wanted to download. So I've got all of them there. It's filled in the range of the longitude and latitude that I've been able to select with that map tool. That's a bit easier than typing it in automatically. And it's selected the date range for me as well. So I can then click on this little button on the right-hand side here, copy that information and just paste it into my Python program if I want to then use that in an API request, for example. So although this can kind of seem quite complicated in the beginning when you're kind of trying to get the hang of using these different interfaces, there are tools available that can help you to put that into a form where it's easier to use. Okay, so let's go back to the slides up. Okay, so I've put in the slides a little summary for you, so you can, if you're going through that yourself, you can remember what the steps were to get through and have access to that interface where you can copy and paste the data yourself. So to summarize about API, so these API, it's like the waiter, it's this intermediary that's going to let your computer talk to the data server so that you can get the information that you're trying to obtain from the data server. So these are a specific type of API called Web API. They're really widely used by these kind of different data centers. And the advantage is that they're going to allow us to select just subsets of the data. So we don't have to download absolutely everything, because normally that's going to be much more data than we need, or that we want to, or that we kind of have the ability necessarily to process. So having too much data can be a problem. So different data centers have different API, but the way that we interact with them is very similar in terms of different software. And often we're going to have these examples that are available to help us to make the request in the format that we need. So a specific type of interface that we often see with marine data, so that you might see, it's more on some of the older data centers now, it's becoming less widely implemented, is called OpenDAP. So OpenDAP stands for Open Source Project for a Network Data Access Protocol. It's a type of API It's been around since for a long time, for several tens of years, and it's so I wanted to talk to you about it because it's often provided by data centers, so it's often a method by which you can access the data. So although it's a generic tool, it's kind of not only used within the marine sciences, but it's very widely used within the marine sciences. And again, the reason why it's been widely used and why it's useful is because it again allows us to select subsets of the data so that we're not having to deal with this problem of having too much data. So because it's been around for a long time, again, it interfaces nicely with kind of lots of different types of software that people in the climate community use. So not just Python, but also MATLAB, CDO, all of these different types of tools. And if you see the term OpenDAP, that can also refer to the community of people that develop it. But we're going to talk here really just about the interface itself. So I'm going to show you an example again of what OpenDAP looks like if we're trying to use it on a web page. So let's go back to close that one. So we want to look at the so this is an example from the IFREMER, which is a French centre that distributes lots of different types of data. So the OpenDAP catalogue, I guess the interface looks quite old now. It doesn't really look as modern as some of the other kind of data catalogues that you might see. And really the structure is that it always looks like a kind of file structure like you might see on your computer. So this is an example. In fact, we're in the threads catalogue here. So you can maybe see on top of the screen, it says threads catalogue. So this is the human interface for the OpenDAP server. So this is a method of accessing Argo data using this server. So we've got the type of data here. It's called Coriolis Argo GDAC OBS. And this list of directories that we have here is the different institutes that have contributed Argo floats to the program. So if I click on Coriolis, we're going to get the French floats that are available via this interface. So that we then get another directory structure. So each of these different folders is going to be the files that's available for one type of float. So if we click on another one. And finally, we get to a point where we've got some files. So this is technical information about the Argo float in this first file here, metadata about the floats in the second file here, and rtraj is going to be trajectory information about the float. So it's kind of less user-friendly than a data catalog in the sense that we need to know what these different files are. So if I then click on profiles, I'm going to get to the point where we have access to the actual data files. And now we can see an example of how the threads interface can help us to choose specific parts of the data. So if I finally click on one of these files, this is a point at which this is information that can, well, a file that contains information that I might want to access. So we've got two methods for accessing it, either the OpenDAP server or the HTTP server. So if I click on OpenDAP, we're going to get onto that access form. So this is kind of part of the catalog method to subset the data, so to choose parts that I might want. So we can see at the top, I've got different buttons so that I can download the data either as a text format or as a binary format. And then each of these, so we've got information here about so it's the metadata telling us about what's in the file. So it's a little bit cryptic. Again, we need to know what we're dealing with before we can maybe understand that. And then underneath, I've got a huge choice of all of the different variables that are available for this file. So if I scroll down a little bit to this one, for example, if I click on station parameters, so I've now got automatically filled in these two little boxes, text boxes here, that are going to allow me to select subsets of that data. So for the number of profiles, it's going from 0 up to 1 in steps of 1. So from that, I can tell that, in fact, there's only one profile available in this file. So it's not very helpful to subset in this case, because I've got a choice of 1. So don't actually have any choice. But for the number of parameters, I can see it's going up to 3. So it's going from 0 up to 3 in steps of 1. So that's telling me that there are different choices of data available for this parameter here. So if I only wanted to download the first 2 station parameters, I could delete that 3 and put 2 there. And now that's only going to retrieve the first 2 parameters for me. Similarly, if I go further down to something where we have depth information, there's lots of metadata for these profiles. Here we are, here's one. So if we go down to M time, so it's telling me something about the time at which the measurement was taken. If I click on this one, so again, there's only one profile, so that's the same for all of the variables, but it's taken 136 different measurements at different depths as it's moved through the water column. So there I might decide that I only want to take the first 10 measurements, for example. I can delete that 136 and put 10. Or another option is that if I want to take all of the measurements, but I don't want to take every single measurement, maybe I want to take every second measurement or every 5th measurement. If I change that 1 in the middle, that's going to change how I hop from one measurement to the next. So if I put 5 there, it'll extract the first depth level, and then the 5th depth level, and then the 10th depth level, for example.
We have a question.
Oh, yes, of course, yeah.
Okay, so it's from Barbara. In the case of the API, since it's using direct access code to yours, it doesn't download any data sets or take up memory, or does it? I mean,
No.
it uses data from the server or the cloud.
So it's going to communicate between your computer and the server. So it will download data to your computer, but it will only download what you tell it to download. So this is why it's an advantage to be able to select subsets of data. It's because if you're storing it locally, you probably don't want to download everything. So it's going to communicate between your computer and the data server, and that won't use up very much data as a process itself, that process of communication. What will use up bandwidth is when it's actually going to download that data at the end that you've requested. Does that answer your question, Barbara? Yeah, okay, super. Yeah. Okay, so with this method here, we would fill in this table to select the different levels that we wanted, or the different kind of subsets of the data that we wanted. Once we've filled in all of that by the graphical interface, if I come back up to the top here, we can either click on Get ASCII or Get Binary, and that's then going to download that data in the format that we've requested, with just the parts of the data that we've requested. So if I click on Get Binary, it's going to download a netcdf file that's going to contain kind of the metadata as well as the actual data. And if I click on Get ASCII, it's going to download a text file that I might need to kind of clean up a little bit in the same way that we saw in the beginning. And then I'll be able to process that data in my computer. Okay, so that's the OpenDAP format. And in fact, so here we looked at the Coriolis website, but in fact, almost any website that you look at that uses this OpenDAP format will have a catalog that looks exactly like this. So they have this very, it doesn't look very modern, right? But they all have this same format where it's kind of fairly simple to use, and you can always have, it's just you click on the button, you put the numbers in that you want, and it's going to give you back that same format. So the advantage is that it always looks the same for whichever kind of catalog you're going to be looking at. You're always going to see the same type of interface. Okay, so up. So the interface that we saw there was what's called the threads catalog. So that's the human part of the interface that talks to the OpenDAP API and communicates with the data server. So threads is an acronym with thematic, real-time, environmental distributed data services. So again, they always have these very catchy acronyms. And in fact, they're just standard interfaces that are going to allow us to extract the specific data that we want to look for. So they give us access both to that metadata via the little piece of information that we had at the top, as well as the data itself via those buttons at the end. So you might encounter them either through older data servers or because you choose to. So often, even if a website provides an API, many of them do still implement OpenDAP and Threads catalogs as well. And in this case, so for our waiter analogy, Threads is going to be like your menu. Basically, it's like you talking to the waiter. And it's kind of your communication with the waiter, and then OpenDAP is the actual waiter part that's going to go and talk to the remote server. Okay. So if you want to use OpenDAP, either you can do that directly through one of these threads catalogs, or a lot of different kind of software that's used in oceanography has a method that will allow you to open access or kind of interact with OpenDAP directly. So you might find that your favorite software has options for you just to enter a web address for an OpenDAP catalog, and then you can interact directly with the catalog via your software. So it might be that your software is able to directly download that data for you. If you're curious to try that, often again, like for the API, there are examples to help you do so. So the Jet Proportional Laboratory, for example, had kind of a series of what they called data recipes that could help you to download these interfaces. And similarly, OpenDAP, the group of developers, maintain a series of links of software that can help you to that interact with OpenDAP, so you can see whether or not it's possible via your favorite software. Okay, so that's kind of the second part of the course, which is maybe still the most common one. It's the case where you're going to be accessing remote data and downloading it to your computer or to a local server in your lab. So the things to remember are that we kind of have these different protocols that are going to help us to get this data to our computer. Some of them are quite standard, so OpenDAP is one of them, and it's widely available. The advantage is, again, that it allows us to subset the data so that we don't have to deal with more data than we need to, and also that we can get the metadata at the same time so that we know what we're looking at. You might do that by one of these threads catalogs, which are quite dated looking, but all work the same way and are kind of fairly easy to navigate. And you can do that directly via your web browser, but also it's possible to do it directly either via software or via a programming language. Okay, so to finish, let's talk a little bit about what happens if we're working with very large amounts of data. So this is kind of really becoming more of an issue in the last 5 to 10 years, I would say. So if you're working with very large amounts of data, probably you're not going to be working on your local infrastructure anymore. And in that case, you might either be working on a supercomputer or you might be using cloud computing. So cloud computing, it's not always very clear what we're talking about when we talk about cloud computing. So the basic idea behind it is that it's you running programs or accessing data that are stored on somebody else's machine and also performing calculations on somebody else's machine normally. And it happens in such a way that everything is very transparent. So cloud computing is normally quite a kind of user-friendly experience. It looks to you as though nothing is different from if you were running the calculation on your own machine. But in fact, there's immense computing power behind it, and it's actually running on either a single kind of array of computers or a series of computers elsewhere that have very significant processing capacity. So supercomputers are normally provided as kind of a research facility by kind of national level infrastructure. Cloud services are often still run by private companies. So there's kind of Amazon Web Services are one of the largest ones, and it's a paid service for intensive use. So this is quite different to the way that we would normally do computing in the research community, which is that normally kind of access to supercomputers is provided by funded national infrastructure, for example. So normally when we are computing or kind of doing large calculations, that's already kind of paid for by research funding somehow. So why is cloud computing becoming more relevant, or why is it starting to be used in science? In fact, it's many of the same reasons that it started to exist in other domains apart from science. So there's been a transformation in demand, which is similar to in the example of e-commerce, for example, or kind of any other industry where there's been more and more data produced. So we have in marine sciences now new data sets that have the same types of requirements, which is that they should be highly scalable. So we want to be able to treat larger and larger data sets. We need kind of more data storage capacity. So these data sets, every time we increase the spatial resolution, they get bigger. And then once we have more data, we need more computer power to be able to process it, because it's kind of requires more memory, more computers processing ability to be able to treat those data sets. And that's true because we've got these new instruments that are providing higher and higher resolution data. So new satellites, for example, are much higher resolution than older satellites, and numerical models are also run at higher and higher resolution. So we've gone from a situation where a model simulation might be of the order of size of a couple of gigabytes to one where a full model simulation can be of the order of several petabytes in less than a decade. So it's orders of magnitude difference in terms of the data size. And so we need new solutions to be able to analyze this type of data. So as an example here, this image that we've got is a simulation that's at 1/60th of a degree of the Mediterranean Sea. So we can see all of these different eddies and current systems that we're able to resolve when we have this very high resolution type of simulation. So it's something that's very valuable to enable us to understand how the ocean's working right down to small scales. But it's quite technically complicated, both in terms of storage, implementation, and kind of producing the simulation in the first place. So if we compare that 60th of a degree simulation with what we might have had in the past with a 1-degree configuration, you can see that we don't have at all the same type of detail in these older type of simulations compared with what we have with these very high resolution simulations. So we've got a kind of very smooth temperature gradient contours in this example here. And in fact, if we compare the Mediterranean Sea, so it's kind of a blurry blob here in this top picture, so we can just see the green region here, that's the Mediterranean. In a 1-degree configuration, that would be kind of, about 40 by 15 points to cover the whole of the Mediterranean Sea. If we increase that to a 60th of a degree configuration, we're up to the order of thousands of pixels to cover the same kind of area. So that's an advantage in terms of what we can resolve. It's an advantage in terms of kind of the different types of physics that we can see in that with those different simulations. But it's really a challenge in terms of the increase in data volume that's going to be associated with those changes. So as another example, if we think about observational data, it's not just model data that have undergone these kinds of transformations. The earliest satellite altimeters, so these were the measurement instruments that were used to measure sea surface height, had a spatial resolution of 1/4 of a degree, which was also kind of standard for ocean models for until quite recently. So that gives us a spatial resolution of about 28 kilometers at the equator. If we compare that with the new instrument SWOT, so that's Surface Water Ocean Topography, it stands for, I think. It was launched in 2022, and the spatial resolution that's associated with that instrument is 1 kilometer. So we're going up by a factor of 28 in each spatial dimension with these new kinds of instruments. So really, it's a huge increase in the amount of data that we might have available. So why are we going towards these kind of higher spatial resolutions? Well, it's because they answer this kind of higher spatial resolution data helps us to answer scientific questions. So with our existing data, we might want to know about things like how energy is transported within the ocean, for example. So it's a really important question for climate is what powers the ocean circulation and how's that energy transported? Where does it come from? Where does it go to? And in fact, we think that very small scale features could be important in understanding kind of the full response to that question. So in fact, to fully understand how ocean currents behave, we need this very high resolution data. But it's also a challenge to know how to work with it. So we're still kind of in this phase of adjusting to understand the best ways to work with these data. So it's difficult because we've got kind of a number of things that are new. So one is the sheer quantity of raw data is much bigger than we're used to, but also the software that we would historically use to analyze our data isn't really necessarily adapted to dealing with these very large amounts of data. So if you have kind of insufficient computing resources when you try and load a very large data set, often what happens is that your machine crashes, right? So if you don't have the correct type of resources available, you just can't do the analysis. So the types of machines that we need to use need to be more powerful to enable us to analyze these large volumes of data. So there's a number of kind of different solutions. So one of them might be that we would perform the calculation on a supercomputer. So these are the types of computers where the simulations are normally produced in the first place for ocean model simulations. So they look something like this image that we have here. So this is a image that was taken from the film The Martian, but in fact it's not very realistic in the sense that normally you don't have to go and attach your computer to the supercomputer like the man does in the film. Right? Normally we just connect remotely in the same way that we've been talking about earlier. So these are these very large arrays of computers that we can use to perform these larger calculations. And what's kind of changing with this increasing volume of data would be that at the end, when the simulation's completed, rather than transferring the final files to local machines, we might continue to perform the analysis actually on the supercomputer. So rather than bringing the data to the machine, we would finish processing the data on the supercomputer and then finally bring the results of the analysis back to our local computer once we have something that's reduced in size sufficiently for us to be able to use it. So in terms of what supercomputers look like, I like this example, which is the Spanish supercomputer Mare Nostrum, which is one of the largest supercomputers in Europe at the moment. So in fact, this is actually housed in an old chapel in Spain. So this is the Barcelona Supercomputing Center, which is responsible for this example. So you can see it's actually quite similar to the example from the film, right? We've got these long rows of servers. So each of these towers that look like kind of large cupboards contains stacks of processing equipment. And if we look from the side up, so you can see all of these different kind of layers within each of the things that look like big cupboards is a processing unit. So each of those individual stacks is going to contain computing equipment. So it can be, we can have storage, we can have actual computing cards that would be stored in stacks within each of these data centers. So this is the side-on view of what that looks like. So basically, just it kind of doesn't look that exciting. It just looks like large cupboards of different computing equipment all stuck together. So we might choose to perform that analysis on the supercomputer if it's no longer going to be possible to perform the analysis on our machine. We might choose to only work with part of the data at a time. So if that's possible that we're only working on a small region, we might choose to extract just that region and bring just part of the data back to our local machines. Or the other option that's being used for data sets that are distributed publicly now is sometimes to use cloud resources. So because we have these kind of larger and larger amounts of data that are available at the same time as people are kind of becoming increasingly interested in artificial intelligence as a method of data analysis, those two have kind of grown at the same time as well. So this kind of, a lot of artificial intelligence requires that you have large quantities of data available. So the fact that we now have these large quantities of data available has started to lead to people using more and more of these techniques within marine sciences. And historically well, kind of still, to implement these types of neural networks or many of these artificial intelligence techniques, we would use a different type of processor to the type of processor that we would use to produce a simulation. So to produce a numerical ocean simulation, often we use what's called a CPU. So it's the same type of computer processing chip that you would have in your computer. For artificial intelligence, often we use a GPU, so it's a graphics processing unit. So it's a type of chip that used to be found, well, it's still found on graphics cards, so that was historically used just for displaying images, but is now often used for performing artificial intelligence computation tasks. So historically, supercomputers that would be available nationally haven't necessarily been equipped with these type of processors. So because people mainly used CPUs like you have in your computer for scientific computing, that was what was available in these supercomputers. That's starting to change now. So more and more of them do also offer GPUs for people to use in scientific research. But until quite recently, the easiest way to have access to that was via systems such as the cloud. So it seems likely, kind of to try and summarize that we're going to need new ways to work with big marine data. So that might be by changing the way that we analyze data so that we're working with it remotely rather than performing the analyses directly on our own local machines. So that's probably going to kind of keep evolving. I say keep evolving because, in fact, actually, this isn't really such a new phenomenon. So we're kind of adjusting now because the quantities of data that we have to deal with are very large. But we've also had to adjust in the past. So, for example, when model configurations that have been used for the past 10, 15 years that are about 1/4 of a degree first started to be used, that seemed like a lot of data at the time. So in fact, there's always this process of adaptation, both in terms of the technology and also the methods that we use to analyze it. And that's probably going to continue to evolve in the future, even kind of after this phase that we're in now of dealing with massive amounts of data has come to some kind of conclusion. So I'd like to show this figure, which shows the amount of data that's, or supposedly shows the amount of data that's available in the globe and how it's evolving over time. So the growth is exponential, right? So, part of it is, people producing more and more cat videos on YouTube and what have you, but part of it is kind of the sum of all available data, right? So we see if we look at the quantity that was estimated, so this is a few years old now, this figure, but they estimated that this year there'd be 175 zettabytes of data that's stored in the world. So 1 zettabyte is about 10 to the 12 gigabytes. So kind of all of our daily lives, as well as kind of all of marine data, all of scientific data, is all contributing to this ever increasing amount of data that's perpetually growing over time. So it seems unlikely that we're going to remain in this situation where we do all of our analysis on our own local computers. One example of that more recently was the CMIP6 experiment. So you may have heard of these types of experiments. They're often cited in the reports of the IPCC. So it stands for Coupled Model Intercomparison Project. It's a kind of big scientific project where lots of different climate centres run simulations that have different forcing of CO2, so different evolution of the amount of CO2 emitted over time, and they look at how the climate responds. And for this, so it's an experiment that's been going on for quite a long time. And for the last round of this experiment, in fact, they decided to distribute this data via the cloud, as well as via standard access methods that had been used in the past, so via OpenDAP or via downloading the data kind of file by file, as some people had done. So this is kind of one example of where we are now. It's kind of this evolution towards allowing people to interact with the data in different ways that's really, I think, probably going to be part of the future of how we interact with these large data sets. So to summarize everything that we've seen, so we've kind of gone from the simplest kind of form of data, but probably the most time consuming to deal with, which is the web scraping application where we're dealing with simple data, through to the largest and most complex. The first example where we're kind of downloading the data ourselves, probably the most time consuming and tedious part of dealing with data. So it's kind of ironically, the part where we have the simplest data is often that which requires the most effort or prior effort by the user. And that where we have the largest amount of data is that where we have maybe the least effort required by the user, because it has to be set up for us to interact with it in a transparent way for this to be able to work. So if you're dealing with small amounts of data up to medium amounts of data, it's quite feasible to manage the process of accessing and processing that data yourself. But once you get onto these larger amounts of data, you're probably going to need some kind of automated system to help you do that. So either via using a software program or using something kind of a remote access option like the cloud services. We've seen that there's different data access models available depending on how you want to access the data. So again, depending on the subset of the data that you want to work with, the calculations that you want to perform, that's probably going to influence exactly what choice you make. And finally, it's really always in a complete state of evolution. So the things that I've talked to you about today probably will have changed within 5 years' time. It's really a kind of situation that's perpetually evolving. So as kind of data evolves, so do the methods that we use to access and treat it. So that's kind of always been the case in the past. That's probably still going to continue to be the case for the future. Okay, so that's the end for me, but if you've got any questions, please don't hesitate. Otherwise, the quiz is no longer at the end. Is that right, Audrey? It's
Yes.
moved to, yeah, okay. Okay.
Thank you very much.
No, thank you. And in that case, I'll say enjoy the rest of the course for everybody and have a good evening.
You too. Thank you very much.
You're welcome.